hear me first of all?
Yeah. Fine.
Yes.
Okay, and here goes my presentation.
Yeah, cool. I think it's fine.
Okay, thank you.
Yeah. So shall we begin?
Yeah, I think it's about time. So in 1 minute or something, you can begin.
Okay, fine. So let's okay. Welcome everyone to the second session of this day. I'm Shumon Chatterjee. In this session, we will have presentations focused on theoretical and observational constraints. So this session is subdivided into two parts. So in the and there will be a break of about 15 minutes in between. So first half, we will have talks by Anshuman, Isabella, and Janakee. And in the second half, we will have talks by Harry, Charlotte, and Stefan, Julian, and Yuxian. So you can ask questions in Slack or in the Q&A here if it is available to you. Or if you are in the panelist, then you can also try raise your hand and ask question. So and in the Slack channel, the relevant thread is 21 CM 20223B, and there are links for every talk available there. Please ask questions there also. I will ask on behalf of you. So without further delay, let me introduce Anshuman. Anshuman from IIT Indore is going to talk about extracting the H1 21 centimeter signal using artificial neural network. So Anshuman, can you start sharing your screen?
Yeah, sure.
Yeah, so I will so you have 12 plus 3 minutes of time. So I will inform you after 10 minutes. That is, you will have a 2 minutes notice.
Okay, thanks. Okay, so hello everyone. My name is Anshuman Tripathi, and I am a second year PhD research scholar in the Department of Astronomy, Astrophysics, and Space Engineering at IIT Indore. And in this talk, today I'm going to talk about the extracting the H1 21 centimeter signal from the cosmic dawn and epoch of reionization from the ground-based observation using artificial neural networks. So, okay, I think there is some problem. I'm unable to switch my slide. Oh, no, now it's working. So during this talk, I will cover the following topics, which I have mentioned here. So let us begin with this picture. So this picture nicely shows the evolution history of our universe from its beginning, when the Big Bang happened, to till present day, and it also mentioned the important timeline of the universe, like the recombination era and the cosmic dawn era and the reionization era with corresponding redshift trends. So let us talk about 21 centimeter cosmology. So in the 21 centimeter cosmology, the observable quantity we measure in terms of the fluctuation of the brightness temperature, delta TB, and this delta TB measures the contrast between the spin temperature TS and the CMB temperature, and based on this contrast, we observe the signal either emission or absorption. And to measure this signal, there are various kind of upcoming and the future coming experiment going on the ground base and the space destination, and they are targeting to measure the signal is in terms of the sky average global signal and in terms of the power spectrum or tomography of the intergalactic medium. So I just listed the experiment name for the single radiometer experiments like the HSRS Bighorn and LDAREs. And for the interferometer, basically, I have listed some experiment name like the LOPAR, GMRT, HERA, MWA, and SK. So apart from this, let us talk about the observational challenges when we are observing this global 21 centimeter signal from the ground-based antenna. So there are various kind of challenges. The first challenge is the high amplitude foreground. So as we know, our signal is very much faint compared to the foreground, and this foreground is much higher. It is 10 to the power 4 order higher than the actual signal. And the other difficulty is the ionosphere. So Earth ionosphere distorts the signal significantly, and it introduced the directional dependent effect. And the detail about the ionospheric effect I will talk in my later slide. And apart from this, there are some other effects like the beam chromaticity effect, radio frequency interference, RFI, and other systematic effects. And in upcoming is the big data side also going to be a big challenge for the astronomers. So yeah, so in my work, actually I have used artificial neural network to extract the global signal parameters along with the foreground and ionospheric parameter too from the composite all sky average signal in presence of the foreground and ionospheric effect. So before going to the detail of my work, let us understand some basic detail about the artificial neural network. So in the layman term, the artificial neural network are computational system inspired by the biological neural network. And the basic architecture of neural network is made up by 3 layers. The first layer where we given input to the model, we call the input layer. And the next layer we call as the hidden layer. And this layer can be more than one. It totally depends upon our problem complexity. And the final layer where we receive the result, we call the output layer. And the dots in the layer represent the neurons. And these neurons are connected with the next layer neurons. And these connections are associated with weight and biases. So if you see in the hidden layer neurons, so in the hidden layer neurons, they are actually activated by the activation function, and outside of the neurons they have no activation function. And if you talk about the process of the how our ANN works, so basically it is working on the 2 methods. So one we call the feed forward process. So the feed forward process, the simple term we call, we can say that it helps to passes the information from one layer to the another layer. And the another method is the back propagation error. So this back propagation principle helps our ANN model to adjust their weight such that error can be reduced. And once our model are trained and validated and tested to evaluate our model performance, we check the by calculating the RMSE score. So the RMSE score basically evaluates the average magnitude of error, and we also calculate the performance by calculating the R2 score. So this R2 score basically evaluates the performance of the linear regression model. So for our work, I have used to generate the global 21 centimeter signal. I have used accelerated reionization era simulation code, and the parameter given to the model are 3 parameters basically. The one is JZ, which represents the Lyman-α background, which determines the strength of the Yuxian coupling. And another parameter we given to the model, it's the ionization fraction of the hydrogen. And the third parameter we given to the model is the temperature of the intergalactic medium. And these parameters evolve as the tan hyperbolic function. So, and for modeling the foreground, I have used log polynomial model to produce the foreground. And here I just use the reference frequency around 80 megahertz, and For our case, I have just restrict our foreground model to the third order of polynomial, and the corresponding parameters are A0, A1, A2, and A3. So let us talk about the ionospheric effect in more detail. So to understand the ionospheric effect in the detail, I have divided the ionospheric layer into three. So the lowest layer we call as the D layer, and this is the nearest layer to the Earth. And the topmost layer we call as the composite F layer. So, and in between D and F layer, there is another layer we call as E layer. So, because of the F layer has high electron density, so and the outer portion of the F layer, the electron density is completely lower than the layer of in between the F layer. So, any electromagnetic rays which is coming passing through the F layer, it got reflected, and because of this spherical curvature of this layer, it deviates the rays towards the zenith. So any ground-based antenna actually record much wider area compared to the original. So, and because of that, we record the antenna record the temperature completely higher than the original one. And the D layer, basically, it has a low electron density, but because it is nearer to the Earth, so it has high density of gas, and the collision of the gas is completely very high, and due to that, it absorbs the signal, and it also emit by the thermal emission. And in E layer, basically, there is no very much. I mean, that effect is not very much significant when compared to the D and F layer. So we are just not considering the E layer. So the deviation for the F layer we calculate using this formula. And here I just plotted the deviation for the tech value T10 XU, which is mid-latitude electron density. And we can see that the deviation is more when the frequency is lower, and it is decreases when the frequency is going to be higher. So we can see that at lower frequency, I mean, these effects are more, and this deviation is also is proportional.
Anshuman, you have 2 more minutes.
Okay, so this deviation, it has actually proportional to the field of view. So it also, we can see that the percentage increase in the field of view also increases at the lower frequency. So I just calculated this thing by using the formula of this. And for the second case, when the D layer, I just plotted the attenuation factor for the tech value 10 tech U, and here we can see the same effect. At the lower frequency, we have higher, and similarly for the thermal emission also. And the final antenna temperature we calculated using this formula. So to train our model, I just created a training data set by using these parameters value, and I just created the 2 cases when we add the signal when we considered no ionospheric effect, and the another case where we add the ionospheric effect. So when we add the ionospheric effect, so we actually have we actually introduce 2 more parameters to our model. So one is tech and another is T. And I just created the training data set by varying this parameter, which I mentioned the detail in the slide. So now once the data set is generated, so I just split our data set into 3 portions, which is randomly selected. So I just take 1 portion for the training as a training, and the second portion as a validation, and the third portion we use for the evaluate the model as a test data. And in the test data set, we add the thermal noise by using the radiometer equation for the corresponding observation time. And this is the flow chart of the work, I mean, that describe like what is the procedure that we have used to construct all the for the training, testing, and all. And here we can see that I just tested our trained ANN model with 180 sample of the test data set and added the thermal noise corresponding 1000-hour observation time. And here we can see that our model predicted the parameters with accuracy of 97% for the signal and foreground also. And for the second case, when we introduced the ionospheric effect, so we again tested our model with the same number of the test data set, and we can see that here our the signal parameters is ranging from 96 to 97%, and for the foreground it's 97 to 98%. And so recently the edges detect the signal, and they found the signal has more depth and flat absorption in comparison of the traditional one. And this can lead to the several possibilities. So the first possibility can be the spin temperature could be lower than the expected one, and another with the background temperature could be higher, and it may be the intermediate, the IGM could be cooler. So based on these edges detection, I just constructed, I just use the data set which have the amplitude which matches with the edges. So here actually I use the semi-numerical code, and the input parameters are different than the Aries model. So here we have used the physical parameters, and now we just follow the same procedure like the earlier. So we just add the foreground to this model and just constructed the first case with where is no ionospheric effect is added, and the second case when the ionospheric effect is introduced. So here we can see that for the second when we have a high amplitude signal. So for the case when we introduce the foreground, so here
maybe Anshuman, you can summarize and conclude.
Okay, fine. So we can see that here for the signal case we are getting accuracy is good, and here when we introduce the ionospheric wave, the F escape is we are getting a little lesser. So and other parameters are very like estimated very well. And in ongoing work, actually, we are planning to add time-varying ionospheric effect into our model to try to estimate the global signal for that. And we also plan to estimate the parameter by considering the chromatic primary beam effect. And we also want to add the real beam patterns, like to understand the real antenna, so that we can apply our model to the more real cases. Thank you.
Thank you, Anshuman. So any questions for Anshuman? You can post it on the Slack or just raise your hand. If not, I can ask a naive question. So Anshuman, how do you check for overfitting? Because ANNs are prone to overfitting.
Okay, so
do you check for overfitting?
Yeah, basically when we are training, so we are just checking the validation accuracy and accuracy. So if the accuracy and validation accuracy is near, they are very much nearer, so we can say that it is not overfitted.
Okay. Okay, thank you, Anshuman. Thank you again, and please ask the question in the relevant sections in the Slack. Anshuman, if you please unshare your screen.
Okay, thank you.
And I'll request Isabella to share her screen.
Hello, everybody. Can you see my screen?
Yeah, perfect. Just make it presentation. Thank you. I'm also seeing the timer thing also.
Okay.
Okay, so next talk will be by Isabella Carucci from University of Turin, and she is going to talk about blind foreground subtraction challenge for SK observatory H1 intensity mapping.
Can you see what can you see now?
Perfect,
Yeah?
perfect. Yeah,
okay, great.
Please carry on.
Okay, morning, hi everybody, wherever you are. So yeah, let's change a bit gear. Now I'm going to talk a little bit about intensity mapping in the post-reionization era with single dish experiments. So the talk is about this blind foreground subtraction challenge that we did as a collective effort of the intensity mapping focus group within the SKA cosmology science working group. So actually, all these people here that are listed are to be acknowledged for the work that I'm going to present to you today. So foreground subtraction, what does it mean? So basically, this is the intensity map that we would like to get. So these bright spots of the order of millikelvin or even less. But actually, this is what we see, right? Very bright and smooth foregrounds, order of magnitude higher than our signal. So how do we go back to this picture if we see this one? This is what is called foreground subtraction. We did this challenge in the context of the SK mid. So forecasting for what the SK mid will do in terms of intensity mapping. And of course, having in mind that the SK mid telescope, we also had in mind Meerkat, which is the SK mid precursors in South Africa. And that is also present doing a pilot survey intensity mapping. So we are collecting data and we are analyzing data. So this is important to keep in mind that what I'm going to say, actually, we are trying them as well on data. I think Alkistis later today is going to tell us more about Meerkat and Meerklas, and also Mel and Steve tomorrow, they're going to present preliminary results with this data. So this is really exciting. Back to the contaminants, which are the real problems in this business. So another way of seeing this is with a simulation. So here I'm plotting the signal intensity as function of frequency. So we would like to see the cosmological H1 here in blue, this noisy line, but we have this very bright astrophysical foregrounds that are also smooth. So one could think about just filtering them out of the cube. That is something like to link to what we have seen on Monday with the CHIME. So also CHIME, it's an interferometer, but as the same foreground. So these are the space, the range in K space that where CHIME has sampled the signal. Here live the intrinsic foregrounds that we should get rid of. The same goes for the single dish. The range in K perpendicular is different, but the foregrounds are the same. So can we just filter them out, or something else is going on? Well, it's not only foregrounds that we have to deal with, but also systematics. Here I'm plotting as an example the polarization leakage, but there are others. So basically, long story short, what happens is that things can happen, and we have contaminants that are of the order of the signal and also are not as smooth anymore as we would like them to be. So can we trust this way of just filtering them out of our data cube? And also the second issue, can we actually hope to get and sample the scales here that are really important for cosmology, but at the moment are dominated by the foregrounds? So under the signal processes point of view, what we are trying to do is a blind source separation process. And the easiest way to think about it is that we have our signal, so some maps in F frequency maps in pixel space. And if we could manage to linearize them in N sources, templates and pixels that are modulated by mixing matrix, then we would have as an output the noise part of this decomposition, which contains also our cosmological signal. So how to solve this inverse problem, ill-posed inverse problem? So we need to assume something. Either we assume that these components are decorrelated, so we diagonalize the covariance matrix. This is called PCA, principal component analysis. Or we can assume independence. The components, the sources are independent, so we need to maximize the non-Gaussianity of them in order to unmix this and get ANS. And one thing to keep in mind is that the thing that we need to set when we play this is the number of components that we want to decompose our data into. And we have proven, and also other people have shown, that the higher is this N, mathematically, the more signal, the cosmological signal you are also removing from the residuals. So basically, you need to keep n as low as possible. So what has happened with observations? So basically, this is what we have in terms of post-TOR single dish observation here. So in 2010, they started with a polynomial fitting, but already the same group 3 years later realized that it was not enough in order to describe this data. Of course, they tried PCA and SEA. On the theoretical side, in all theoretical works, there was no noteworthy difference between PCA and SEA, and 4 components were enough in order to do the job. In real life, people had to at least remove 10 or higher components, Anderson et al. 10 as well. And most recently, in 2021, still with GBT data, they did an analysis with up to 36 components removed from the data. So really, there is a mismatch between what we have in the data and what we know how to simulate and we know how to model. So in order to move the field forwards, we need simulations as realistic as possible. That is something that people have been working a lot and still are working. Here I'm just listing some of them about satellite contamination, 1/f noise, beam modeling. Then we need new blind source separation algorithms optimized for the scope of doing H1 intensity mapping. And this is me and other people have been working. Of course, here I will focus on the method that I work on, which is called mixed GMCA. I will come to a second to it. So a quick interlude on GMCA. So a third assumption you can use in order to solve this is sparsity, because mixture are less sparse than source. What do we mean by sparsity and why this is always true? So a signal is sparse when I can find a domain, a projection where my signal can be described by really few components. So the classical example is if you have some data that looks like a sine wave, then you go to Fourier space, and it becomes sparse. It's the same data, but now it's sparse. So if you manage to do that with all your sources, then their mixture, that is what you start with, is less sparse than the individual sources. So maximizing sparsity when you do this decomposition makes it easier to disentangle the different components. In this context, we deal with things like the galactic synchrotron. Where does it, where is the space where the synchrotron looks sparse? It's not in pixel space, but yes, if we work in wavelet space, things become much sparser. And this is what behind GMCA, general morphological component analysis. First, we wavelet decompose the data, and then we use this sparsity thing in order to disentangle different components. And it is, I mean, we already shown that it works very good on this kind of data. But to move forward, one other thing that we realized is that different scales need different care. This is really evident with data, actually. So this is GBT data using FastSEA to remove components. So this is the power spectrum of the residuals, the maps where we believe there is a cosmological signal left. So you see the black line is the residual with just 2 components removed, and then I keep increasing the number of components I remove, and this signal goes down. But really, there is a lot of scratching in the large scale side of this plot, not so much on the small scales. So basically, probably we are even overfitting a little bit on the small scales. So here the idea of using PCA on the large scales, where I have my really diffuse foregrounds, astrophysical foregrounds, and then GMCA just on the small scales, where I know there are many defects in the maps because of systematics and so on. So, and this is mixed GMCA, basically. So here now my list is complete. We have the simulations, we have the pipelines we want to test. We need to put all together in order to test all the pipelines on the same set of simulations in order to understand which one is working well in which context and so on. And this is basically how it started the first blind foreground subtraction challenge. So we asked ourselves, if we were given some SK mid intensity mapping data today, what could we achieve in terms of combinant subtraction with the pipelines that we currently have? So we tried to simulate all we could in the best way we could. So sky components, we had a very well realistic simulation of H1, and also for the astrophysical foregrounds, we had both the Gaussian realization and the more realistic with using the Planck sky model, spectrally varied spectral index for the synchrotron, and so on. The details, I cannot enter into details today. We had the telescope beam. Also for the telescope beam, we had the Gaussian approximation as well as a modified error beam, both having in mind the characteristic of the SK mid and Meerkat. And for the scanning strategy, we use the one that we are using at present with Mirklat in order to have a non-uniform noise in our maps. So at the end of the day, we had 16 dirty data cubes to clean. We looked at this region in the sky using the frequencies and the region that we are looking on with Mirklat. So Mirklat is coming back many times here. So here is how our like one of these 512 maps that we had, how it looked like, and this is how the cosmological signal and the noise look like. And this was unknown to participants. So the participants participated using these different 9 pipelines. So we had the different flavors of PCA. So even something really standard as PCA, according to the different preprocessing you do, they actually led to pretty different results. So different PCAs, the 2 fast SEA pipelines, the GMC and mixed GMCs that I discussed, and also polynomial and parametric fitting. It was a really
we have 2 more minutes.
Okay, great. It was a really serious blind challenge. So actually we did also our analysis blindly. We assigned to the clean data cubes animals names for 1 year. We kept having these telecons. We were discussing things like the armadillo cube as a problem sort of things, but I'm going to present the unblind results. At this point, we compare the results at the map level. So in terms of angular and radial power spectrum. So here I'm showing the input H1 plus noise angular power spectrum in frequency that we would like to retrieve, and what we had in the dirty cubes. Same thing for the radial power spectrum. So it's really all my foregrounds are really correlated here. I have a lot of power in the larger K parallel modes. A little bit of results. We had plenty of results, 9 pipelines on 12 data cubes. But basically, so here I'm showing the relative difference in terms of angular power spectrum. So white means it's good. Red, we are overestimating the power spectrum. We had problems at the edges of our cube, especially the low frequencies where the noise is higher. And we also had stripes here in different gravity and different shapes according to different methods. But basically, we had sort of the fringes, especially when we had the more realistic beam. And then we also had things that we didn't understand, like here I'm showing for the parametric method, it was performing really well for the high frequency channels, not so well for the low part, but here there are a bunch of channels where it was working well as well. So we had a lot of results so here I'm showing again the equivalent of these fringes in this angular power spectrum plots. Here is for the radial power spectrum, we had these peaks appearing where we had the realistic beam, basically because of the interaction of the beam with the side lobes and our spatially varying foregrounds. So this feature was appearing, and we discussed a little bit in the paper. So a lot of results, we decided to compress them in radar charts. Here an example of these radar charts. So basically we had 7 metrics, 4 belonging to trying to describe the radial power spectrum. So in terms of what's the minimum K at which our results are not farther than 30% from the true one, the RMS, something describing this peak, and the same also for the angular power spectrum. We had 512 channels, so we had the variance of this RMS and the number of angular scales where I could trust the recovery of the angular power spectrum. And these are some of the results. So you can see they are really different from each other. Even things like PCA, they behave very differently. So we are starting to see that, like, which of the preprocessing steps we are using are actually matter in this game. Also the N foregrounds, so the number of components that we remove was different from participant to participant, and it played the game. Just wanted to point out that here mixed GMCA with just 4 components is performing really well. And it's like the best of the 2 parent methods it belongs to. So GMCA and this PCA here on the top. So it's really taking the best of the 2 things that possible. So summarizing, it was an excellent exercise, this blind challenge. We are keeping working on this, both in terms of making a new challenge, but also doing some cosmological inference on these cubes that we have and so on. We discover many things. We realize how important it is to do a proper deconvolution of the beam. Small differences in implementation lead to quite different results. Many different needs to be investigated. All these things are going to be tested on mid-class because it's ongoing, and we are learning many things also in that point of view. And I just want to conclude that this is very critical because intensity mapping is one of the highest priority surveys in terms of cosmology for DSK. So we need and we will be ready for this. And I said all I wanted to say. Thank you.
Thank you, Isabella, for this nice talk and great overview. So, floor is open for question now. So, any question for Isabella? Maybe by the time people are gathering their thoughts, I can ask you a naive question. So, these results that you are showing is for single dish mode, right?
Yep.
So, so for the SKO also you plan to do it in the single dish mode, or you have plans for interferometric mode?
Well, the SK mid for a redshift below 3, yes. Basically, in order to reach the cosmological scales that we would like to reach with intensity mapping, the way to use SK mid is with in single dish mode. So yes, we plan. The plan is to use SK mid as a single dish intensity mapping machine.
Okay. Any questions from the participants? So, how does the signal look in the wavelet space? And
in which space? Sorry.
Wavelet space. You showed that your foreground is quite sparse in wavelet space.
Well, the signal doesn't look sparse because it's uniform. It's really like noise, right? I mean.
Oh. Okay.
So in wavelet space, it's not sparse. This is the answer.
Okay, so I don't see any question for you. Maybe people will ask in later time in Slack. Please,
yeah, sure.
If you kindly look into the Slack in some time. Yeah. So thanks again, Isabella. Yeah.
Thank you.
Janakee, could you please share screen? Yes. So Janakee, I will let you know after 10 minutes that you have 2 minutes more. So it would be in a 12+3 format. So, so next talk will be by Janakee Raste from Tata Institute of Fundamental Research, and she will discuss about the implications of Lyman-α forest in redshift 5 to 6 for 21 centimeter observations. So over to you, Janakee.
Thank you so much. So hello everyone, I am Janakee. I'm a postdoctoral fellow at TIFR Mumbai, and well, I would like to begin with thanking the organizers for giving me this opportunity to talk about my work today. And this work was done in collaboration with Girish, Catherine, and the few others. So today I'm going to talk about what is the implications of the Lyman-α forest on the observations of the 21 centimeter signal from the Epoch of Reionization. So just a moment. Let me begin by giving a brief overview of the cosmic dawn and Epoch of Reionization the way we see it, that the first sources of radiations formed in the overdense collapsed regions, and they started emitting ultraviolet radiations which ionized the surrounding medium. However, when did this happen, and at what redshift, and what were the sources of these radiations is still a question which we are trying to answer. And some of the most important tool for that is simulations. So for that, I'm going to talk about this simulation model given by Kulkarni et al. In 2019, and which basically gives us a history of the reionization, where the reionization ends by redshift around 5.3. What is special about this reionization model is that it appears to be in concordance with all the observation probes which we currently have. For example, Lyman-α forest, Lyman-β forest, IgM damping wing observations, etc. CMB reionization optical depth. While it is beyond the scope of my talk to discuss all of these observations currently, but I will mention a few, and then I will go on to discuss the implications of this observational probes on the 21 centimeter signal. So the first probe is the basically Lyman-α effective optical depth. So when we observe spectra of distant quasars, some of its photons blue out of Lyman-α has been absorbed by intermediate neutral hydrogen in the IgM, and we can learn a lot of properties of the IgM by observing this spectra. So one of the things which we observe, which we notice in this quasar spectra, is that when we observe quasar spectra of this at the same redshift but in different parts of the sky, they appear to have a very different absorption troughs, and that gives us idea that maybe the universe is very inhomogeneous in terms of the neutral hydrogen presence in different parts of the sky. So for example, this one shows a quasar spectra of redshift 6 for two different quasar. To quantify this effect, we can define something called the effective optical depth. So basically, effective optical depth is the ratio of the flux that we observe over the ratio of the flux which we expect, unobserved continuum. So this effective optical depth has been plotted from all the various quasar spectra by Becker et al. And Bozeman et al. And what we observe here is that not only optical depth increases as we go to higher redshift, from redshift 5 to redshift 6, but its scatter also increases, which means that going from redshift 5 to redshift 6, the intergalactic medium not only becomes more and more neutral, but also the neutral fraction becomes more and more inhomogeneous. This particular observation was difficult to explain by just the density or temperature fluctuations in a post-reionized universe. So for that, it was necessary to, which was noticed by this Kulkarni et al. Model, was that the reionization had to be postponed to much lower redshift, by redshift 5.3. And by doing so, this particular model is able to explain these observations beautifully. Also, we also see that this is in agreement. This blue curve corresponds to the ionization history given by Kulkarni et al. Model, so which I call late ionization model for the rest of the talk. It is in agreement with almost all the other observational probes of the IgM that we have at this redshift range between redshift 5 and 8. And it is also in agreement with the CMB reionization optical depth by Planck 2018 data, which also predicts a late reionization. So as seen here, the reionization midpoints happens around redshift 7 and reionization ends by redshift 5.3. Now, before discussing the implications of this on 21 centimeter signal, let me just give you a brief overview of the simulation setup. The simulation was done in two parts. In the first part, we use a hydrodynamical simulation in which is P gadget 3 code is used for that, which is a modified version of the gadget 2 code. And we use 2048 cube dark matter as well as baryonic particles. This generates the density and the velocity fields. On top of that, we run A10 radiative transfer code to generate ionization and temperature fields. This simulation has very large dynamical range, start from around 80 H inverse co-moving kiloparsecs to 160 H inverse co-moving megaparsecs. And this has been used, GPUs have been used for parallelization, etc. So now let me finally come to the main point of this talk, which is the implications for the 21 centimeter signal. If the reionization is patchy and late as predicted by the simulations and a lot of other observational probes, what does it mean for the 21 centimeter signal? Now, I will not go into detail about the 21 centimeter signal itself, but I'll just like to point out that the 21 centimeter the signal depends on ionization, density, spin temperature, and velocity of the IgM at a given redshift for a given cosmology. But in our work, we have ignored the fluctuations caused by spin temperature both for the sake of simplicity and also because we wanted to understand the effect of ionization history on the 21 centimeter signal. Now, if our assumptions are wrong, that if the spin temperature has not saturated, in that case, we will have our results, our predictions are conservative because there will also be fluctuations because of spin temperature. So ignoring this effect, let us just see what does the ionization history look in terms of the 21 centimeter signal. So on the top, I'm showing the ionization history. On the bottom, it's the corresponding 21 centimeter signal. So because we have ignored the spin temperature fluctuations, we can see that it corresponds beautifully with the ionization fraction of the IgM. And we have large 21 centimeter brightness temperature fluctuations at redshift as low as 5.5, which is what we expect, which results in large power spectrum at redshift, at even low redshift. So here we compare power spectra for two different reionization models. The first one is a late reionization model, which is the solid lines. And the second one is the early reionization model, in which the reionization ends by around redshift 6.7. So comparing these two at redshift 9, we see that, which is the blue curves, we see that they have the same order of magnitude amplitude, but their shape is slightly different. However, at redshift around 5.6, we see that there is a huge order of magnitude enhancement in the power, both in the ionization and the 21 centimeter power, which is of more importance to us. And this is kind of encouraging for us because this makes us, because the observational prospects at lower redshift are slightly better because of improved synchrotron characteristics. So because we have weaker foregrounds at higher frequency, which corresponds to lower redshift, we decided to see how does this affect the 21 centimeter sensitivity of the instruments for our predicted signal. And for that, we used 21 centimeter sense, which is in a publicly available code, and we calculated sensitivity for 4 different instruments. I'll talk about that in a moment. For 1080 hours of observations, 8 megahertz bandwidth, and we assumed that the foregrounds have been removed moderately, which means that there is, we have ignored the horizon wedge from our calculations, but we have assumed that the rest of the ER window is clean and all the modes are available for the sensitivity calculations. So these are the 4 instruments which we have considered in our sensitivity calculations. So Hera, MWA, and LOFAR are already observing, and SK is coming up in the decade. So we have, this is a very crowded slide, and before going into detail about any of this, the only point I would like to mention here in this one is that all these instruments in principle have the frequency range to observe 21 centimeter signal between redshift 5 and 6, though none of them currently do take observations in this redshift range. And finally, what are their sensitivities? So we see that for 1080 hours of observations, yes, Hera and SK can observe our enhanced 21 centimeter signal, which has been predicted from the Lyman-α forest and CMB spectra data.
Janakee, you have 2 more minutes.
Okay, thank you. However, what again I would like to point out here is that even though we have the capability, none of the observations have yet taken place in this redshift range, redshift between 5 and 6. And that was because traditional models of reionization predicted that the reionization would end way before redshift 6. So people did not plan observations at lower redshift probably. But I would like to point out that there is large signal at redshift, this redshift range, and the sensitivities are better. And there is a lot of other observational probes available at this redshift range, which leads to synergies between at this redshift range between 21 centimeter and other observational probes. So instruments should try to focus on this redshift range, redshift window, which is still very unexplored. Now, I don't have time to discuss anything in detail about other higher point statistics like bispectrum, but in an upcoming paper, which we will be submitting in maybe a month, we are discussing what are the prospects of bispectrum detection in this redshift range at between redshift 5 and 6, and specifically what are the probes of what are the possibilities of observing the neutral islands which are highly non-Gaussians in bispectrum. I can't discuss the bispectrum, but let me show the bispectrum results. And Basically, again, in the blue, I'm showing the bispectra, isosceles bispectra at for our late and early reionization models at redshift 9, which is the blue, and redshift 5.6, which is red. So what we see is that there is still even large bispectra at this redshifts, and because they have very different characteristics than 21 centimeter power spectrum, it would be interesting to focus on this particular statistics as well. I think I will leave with the summary, and thanks a lot for listening.
Thank you, Janakee, for the talk. And floor is open for question now. Please ask your questions in the Slack, or you can raise hand here. I can. Okay, by the time people are gathering their thoughts, I can ask you a very nice question. So I see that when you compare your power spectrum at different redshift in the last sort of summary plot that you have shown, it increases near 6 in all the scales. Why is that? Here, yeah.
Yeah, I think it's because mostly the fluctuations between 6 and 7 are the largest, redshift 6 and 7. And because we are only considering the ionization fluctuations, because if you had also spin temperature fluctuations, they would be larger at larger redshift. Whereas because we don't have that, the power decreases at larger redshifts because the universe is mostly ionized at this, neutral at this redshift. So it peaks here.
Right. Okay. So we have a question from Harold. So does your simulation contain a subgrid model for small scale absorbers along the line discussed by Yuxian?
I don't think it, no, I don't think it has any subgrid absorbers.
Okay. So, okay.
Thanks for the question.
We have another question from Joe. So is the difference between the power spectra at the same in both models if you compare them at similar stages of reionization, that is similar XH1 instead of similar redshift?
Actually,
so,
no. I had a plot probably for showing the ionization. I'm not sure if I have that or yes. Yeah. So if you see, yes, it does look very similar. That you might say that probably the ionization history has just been shifted to a lower redshift. You can maybe say that. However, there is. Yeah, so that does happen. However, if you compare them side by side, we see that there is a lot more neutral islands on the late reionization models where, compared to the early reionization model. So this is early reionization model. So they would not have exactly the same power spectra, but yes, they have similar shape. The small scale effects are different.
Thanks, Janakee. Thanks for the talk, and I will ask other to ask the question in the Slack. And if you please look at the Slack sometime later, you may find some more questions.
Thank you.
Yeah, so we'll have a break now for maybe 10 minutes or so, and we'll come back. So in the meantime, I will request the other speakers.
Janakee, can you please unmute?
Yeah. Janakee, could you please mute yourself?
Yeah, so we can.
Test. So So Harry, could you please share your slides and discuss
Hey.
the audio?
Sure thing.
Yeah, hi.
Can you see that?
Yeah, cool. Could you,
Can you make it full screen, please?
presentation?
Just give me a second.
Yeah, sure.
Um, yeah, can you see that? Okay.
Yeah, it's fine.
Nice. All right.
So
Maybe I should also try.
Yeah. Could you please share? Yeah, it's cool. It's cool. Yeah.
We also have two more speakers speaking. Like just
Yeah.
after me.
I'm waiting for
Stefan is
Julian.
here.
Yeah, I can see
Stefan?
Stefan. Yeah.
Yeah.
So
Stefan, can you
how-
unmute yourself? Sorry. Can you
Yeah,
unmute
please.
yourself and just check the audio is working or not? Stefan.
Yeah, I was. Can you hear me?
Yeah,
Yeah,
we
it's-
can hear you. So
yeah,
how
fine.
you guys will
Yeah,
collaborate?
I will
Like,
just stop share and Stefan will start sharing. It should be quick. Maybe you can give a try.
I was gonna say I'll try briefly after you.
Yeah, like blah blah blah. Then I finish, just stop sharing, then you can start sharing.
yeah, it means like you will manage, right? I don't have to interfere or anything.
No.
Cool. That's fine. That's reasonable.
You can see this as well.
Yeah.
I think Julian will join us a little bit early.
He texted me. Yeah, he will join just before talk time.
Okay, then I'll check this one
Yeah, Charlotte.
from my side. Charlotte.
Yeah.
Okay, so let me share my screen. Share screen.
Okay, so first, who's going to take? Stefan, Yuxian, or?
No, I will start.
Okay, fine. Thank you.
I think I will introduce all of us. So you can just say some people from Hera is gonna present their results. That is fine.
Cool. Okay.
Can you see the video?
Yeah, I can see the video.
My name is
Yes.
Charlotte Mason.
And the audio is
at
fine.
the Cosmic Dawn Centre at the University of Copenhagen. And today I want to talk to you about what we can
The
learn
quality is
about
highest
both
720.
astrophysics
so I
and
cannot-
cosmology from 21 centimeter observations.
Yeah.
In particular, how we can make forecasts for this using vision matrices.
Yeah. Okay. So I think we'll take a few minutes. Yeah. We'll start around 6:18 or something. Sorry, GMT is 12:48 or something like that. Hi, Julian. You can try sharing your screen once if you like.
Okay.
Yeah.
Let me do that. Does this work?
Perfect.
Great, thank you.
Yeah. Yeah, maybe we can start the second half of this session. So welcome everyone to the second half of this session. We will have 3 talks in this session also from Harry, Charlotte, and there will be a talk by Hera Group, which will be delivered by Stefan, Julian, and Yuxian. So you can ask questions in the Slack. The relevant link is 21 centimeter 20223B, and there are links available there. You can ask them in Q&A here. So speakers will have 15 minutes for the first 2 talks, and the third talk will have 20 minutes. So they are divided in 12 plus 3 and 15 plus 5. So the first talk will be by Harry Thomas Jones Bevins from Cambridge, and he is going to talk about a comprehensive Bayesian reanalysis of the SARAS-2 data. So over to you, Harry.
Hey, can you see that okay?
Yeah.
Okay, nice, thank you. So yeah, I'm Harry. I'm a third-year PhD student at Cambridge, and I'm going to talk to you about a Bayesian reanalysis of the SARAS-2 data. So we're trying to constrain the parameter space of the global 21 centimeter signal from the EOR here. And this is work I've done in collaboration with my supervisors and then with some members of the SARAS collaboration as well. And the paper is available on archive for you to go and have a read, and it's been submitted to MMAS as well. So just a recap on where this data has come from. So it's collected with this short monopole antenna that's designed to have an achromatic response. And that data is modulated by the total efficiency of the antenna, which accounts for the coupling of the sky to the antenna beam, and then for any impedance mismatch between the antenna and the transmission lines to the electronic backend. Assuming the presence of a 21 centimeter signal in our data, then our antenna temperature is given by the sum of that signal and some foregrounds, or multiplied by the total efficiency of the antenna, which gives us a spectrum that looks like this on the far right. And this data has previously been analyzed in 2017 and 2018. So in the original work, they used a likelihood ratio test to determine whether any of a set of 260 models was present in the data. And then later on in 2018, they fitted the same set of models multiplied by a scale factor to the data and used the value of that scale factor to determine whether the signals were present in the data, and if not, how significantly they were rejected. So you can see some example signals here, and you can see that the rejection significance was quite high for a number of these signals. So having said all of this, you might ask, why are we looking at this again? What are we doing differently? So here we are looking at using a full Bayesian framework, implementing our fits with nested sampling and polychord. We've got data signal models here, so including some of the additional effects like Lyman-α heating and CMB heating that Anastasia discussed this morning, and that weren't present in the simulations used in the original analysis. And here we are using trained neural networks to emulate the global 21 centimeter signal. So we're not restricted to a set of 260 models, but we can generate signals across a broad range of the parameter space. We're using smooth foreground models here based on maximally smooth functions. So previously, they used unconstrained polynomials to fit the foreground. And the application of these smooth foreground models allows us to identify a non-smooth systematic in the data and then separately model that from the foreground. We assume that the noise in the data is Gaussian distributed, and then we look at several different models for the standard deviation on that noise, and there's much more about that in the paper. I'm not going to spend too much time on it here because of time constraints, but you can go have a read if you're interested. So to look at a few of these model components in a bit more detail, when we are fitting the foreground here, we're really fitting the foreground multiplied by the total efficiency. And as I said, we're using a variant of a maximally smooth function here. So these functions have their derivatives constrained so that they do not cross zero. And this prevents the introduction of non-smooth structure into the foreground model. In our case, because our data has an inflection point in it, we constrain derivatives of order 3 or greater. So we're not introducing high order non-smooth structure to the model, but we are allowing that inflection point to be fitted. So the foreground model actually struggles when we're trying to fit the entire data set, possibly because of this turning point at very high frequencies. So what we do is we fit the data between 110 and 180 megahertz. And when we look at the residuals from that fit, we see this sinusoidal structure, which we really need to model if we want to provide parameter constraints on the global 21 centimeter signal. So in terms of modeling that systematic, we think of this systematic as entering the system in 2 different places and model those systematics separately. So the first is a systematic introduced prior to the antenna. So this could be things like ground emission. And you can see from this equation here that this is a damped sinusoidal systematic multiplied by the total efficiency of the antenna because it's passing through the antenna and into our data. We refer to this systematic as the efficiency systematic. And then separately, we model the systematic as a damped sinusoidal function introduced in the electronics, essentially, of the radiometer. And you can see that the difference here is that one is multiplied by the total efficiency and the other is not. And we would hope that our analysis will be able to pin down which of these is preferred, and then that will help us identify a cause of the systematic. So this non-smooth systematic is just an additive term to our antenna temperature when we're fitting the data. In terms of signal modeling, we model 2 different types of global 21 centimeter signal. So the first, which we refer to as standard astrophysical signals, just has a CMB radio background, and you can see some examples of that on the top of this graph here. And of course, the signal is passing through the antenna. So when we're fitting this, we're multiplying it by the total efficiency. And you can see that that reduces the amplitude of our signals and gives them this structure. The second model that we're fitting is an excess radio background model, where that background is coming from high redshift radio galaxies. And these models can reach much deeper absorption features, and they were kind of designed to explain the edges detection. And again, we have to multiply them by the total efficiency when we fit them to our data. So as I've already said, we're using global EMU to train neural networks on semi-numerical simulations, which allows us to physically model the global 21 centimeter signal. And these models rely on this set of astrophysical parameters. So these are things like the star formation efficiency, the X-ray production efficiency, and the radio production efficiency of these high redshift radio galaxies. And these are the parameters that we're really trying to put constraints on with the SARAS-2 data. So there's a lot going on here. We have 3 different noise models for that standard deviation on the Gaussian noise. We have 2 signal models, 2 systematic models, and obviously we can fit without systematics and without signals. So what we do is we perform a number of different fits with different combinations of these model components. And then we look at the log evidence to try and determine which of the components are favored in our analysis. What we find is that there's not really a preference for a signal in the data, which is kind of to be expected from the previous SARAS-2 analysis. And this graph is showing you the type of systematic based on the marker, and then the type of noise model based on the color here. And you can see that there's some uncertainty in the systematic modeling and in the noise modeling as well. So to try and kind of overcome this uncertainty in these model components and derive constraints on the astrophysical parameter space, we take fits with common signal types and combine the samples from our nested sampling runs and then look at the astrophysical parts of the parameter space. And when we do this combination of the fits, we weight the fits samples by their Bayesian evidence. So we can look at those weights. So here you can see that I've split the fits based on their excess radio background signals and standard astrophysical models. You've got the noise type along the bottom here, and then the weights on the y-axis. And you can see that the efficiency systematic is consistently favored because it has a higher weighting over the damp systematic. And remember that the efficiency systematic here is power introduced before the antenna. So that kind of indicates that this systematic might be from ground emission, for example, or it could be induced by variation in the ionosphere. There's still a little bit of work to do to kind of pin that cause down. But nonetheless, once we've combined our samples, we can go ahead and look the theories here are also very flat, a functional prior, and comparing that to the functional posterior shown in here in red. There are minor differences here, but there's nothing to suggest that we're significantly constraining the parameter space.
Sorry, Harry, we lost you for last 30 seconds or so.
Okay, I can just repeat this slide then, if you can.
Yeah, sure. Yeah.
All right, sorry about that. So I was saying that for our astrophysical parameter space, for the standard models, our 1D and 2D posteriors are very flat. So we don't actually constrain this parameter space. And you can confirm that by looking at the functional prior and comparing that to the functional posterior, where you see a few minor differences, but there's nothing significant here to suggest that the SARAS-2 data is constraining this parameter space. However, when we look at the exotic astrophysical models, again, you can see that the 1D posteriors are very flat, but there are some regions of the 2D parameter space that are less favored. For example, combinations of high F radio and low FX, and high F radio and high F star. So remember here that F star is the star formation efficiency, F radio is the radio production efficiency of those high redshift radio galaxies, and FX is the X-ray production efficiency. So it's not abundantly clear looking at this corner plot what kind of signals this corresponds to. So comparing a functional prior again with a functional posterior shown here on the right, we can see that the SARAS-2 data is actually ruling out the deepest of these excess radio background models.
You have 2 more minutes.
Okay, no problem. Thank you. So yeah, we're constraining these combinations of F star, F radio, FX, and F radio. So to conclude then, we've identified the presence of this systematic in the data that could be caused by ground emission or ionospheric effects, for example. But despite the presence of this systematic, we are still able to constrain an excess radio background above the CMB with the SARAS-2 data. And we actually see some agreement with the recent HERA analysis. And I have an additional slide on this if anyone has any questions. We disfavor this combination of F star and F radio, and then separately FX and F radio. And as I said, this corresponds to these very deep exotic astrophysical models. So the paper is available on arXiv for you to go and have a read. And there's some links to the softwares that we've used in this analysis. thank you very much for listening. I'm happy to take any questions.
Thank you, Harry, for the nice talk and analysis. So we already have a question in Slack. Let's go to that first. So Yuxian asking is that if physical model, okay, he can ask the question here also.
All right, yeah. So yeah. I was just wondering, so because you are using the physical models and the physical models don't reproduce the flatness that we saw in Aegis results. So yeah. I was just wondering if you can, or if you have tried to just use their fitting functions as a signal and redo the analysis.
As in fitting a flattened Gaussian to the SARS-2 data?
Yeah.
We haven't tried this. It is something we could look at in the future, for sure. Yeah, it's a good suggestion. Thank you.
Any more questions for Harry? So maybe I can ask the naive question. So do you have actually in the data that you are analyzing, you don't have that turnover, right, in the dip?
What do you mean, sorry?
The data range that you are actually analyzing, it doesn't have that 100 megahertz, dip near 100 megahertz
in the global 21 centimeter signal.
Yeah, right.
Yeah, so you can see in the bandwidth here, 110 to 180 megahertz.
So does it make life difficult when fitting foreground because you don't have that turnover?
Yeah, it definitely doesn't help. If we had more non-smooth structure in the data, we would expect to potentially get tighter constraints. The biggest problem with the SARS-2 data is the magnitude of the signals after you multiply them by the total efficiency of the antenna. It's kind of comparable to the noise, which is why we don't really get constraints on the standard astrophysical models, but we see tighter constraints on the excess radio background models because their magnitude is comparable, greater than the noise, if that makes sense.
Okay. So any more questions for Harry? You can ask, we have some time. Yeah. Maybe people will ask question in the Slack channels. Please have an eye on that.
Yeah, okay. No problem. Thank you.
Yeah, thanks, Harry. Thanks for the talk. So we will move on to the next talk, and it's a recorded talk, and by Charlotte Mason, and she's going to talk. The recording is about in cosmological and astrophysical inferences in cosmic dawn 21 centimeter observations. So you can ask the questions in the Slack, and the speaker will appropriately answer the questions at a later time. Yeah. I think we can start the video.
Hi, my name is Charlotte Mason. I'm at the Cosmic Dawn Center at the University of Copenhagen. And today I want to talk to you about what we can learn about both astrophysics and cosmology from 21 centimeter observations, in particular, how we can make forecasts for this using fission matrices. So the motivation for this work is really that, as far as we can tell, dark matter seems to be cold and collisionless, but we still have no idea what dark matter actually is. And you can see this here in the matter power spectrum, where these observations are plotted against a model that we would predict from cold dark matter. But there are many interesting dark matter candidates that would deviate from this cold dark matter model on small scales. So we'd like to be able to test what the matter power spectrum looks like on very small scales. And you can see here, we can do this with the Lyman-α forest at lower redshifts. But what we would like to be able to do is to push this to smaller scales. And we think that potentially 21 centimeter observations may be a way that we can do this. So the sort of big picture goal is, how does dark matter behave on very small scales? And what I want to try and persuade you a bit about today is that we think we can answer this question by understanding when and how the first galaxies formed, and then how do they affect their surroundings, which is what we see in our 21 centimeter observations. And so this is because as the first galaxies will form in the lowest mass halos, by understanding when and how the very first galaxies formed, we think we should be able to learn something about these very low mass halos. And so really the early universe then becomes a sort of lab for testing our models of dark matter. And so in this work, we've been using the ethos effective theory of structure formation simulations, which are really a suite of simulations that include a range of different dark matter models, basically all models where dark matter is able to interact with either itself or with some kind of dark radiation. And what you're seeing are just 4 simulations from the ethos framework. And so basically in each simulation, dark matter behaves in a slightly different way. And these types of simulations will give us different predictions for the abundance of halos in the early universe. And so that's what we can see when we look at the dark matter halo mass functions. And basically different dark matter models will suppress structure formation differently, and that will imprint on the dark matter halo mass function. So there's a lot going on here, but basically each panel is a different halo mass functions with a different dark matter model, where basically models going from top to bottom. The models at the top are basically warm dark matter models where there's very strong suppression of mass at different scales. And going towards the bottom, these models have strong dark acoustic oscillations, which would arise if dark matter can interact with a dark radiation particle, which will cause oscillations in the matter power spectrum. And you can see that show up as sort of wiggles in the halo mass function. And then from left to right, basically, we're just changing the scale at which this suppression becomes important. And so going to the far right, this mass scale moves to very, very small scales, and it effectively converges to CDM. And basically, all of these different models will then do, depending on what universe we live in, these would all do different things to affect the 21 centimeter signal. So what does that look like, for example, in the global signal? So this is a fiducial sort of example, cold dark matter global signal. But what happens if we change the dark matter model? And so what I'm going to show you now is if we now have a warm dark matter universe, which is shown here by these yellow lines, where basically the difference between the solid and the dashed is just the scale at which the suppression of halos occurs. You can see that this really can delay this 21 centimeter signal and also change its amplitude. So for example, this one to the left here, the solid line, low mass halos are really suppressed. So that delays when the first stars form, and obviously then delays the global signal. So these are just the warm dark matter models. We can also fill this in with this kind of range of different dark matter models that I was showing before from the halo mass functions. And there's a whole kind of span or range that these models can span. Some of this has been shown before by Julian. But the question is then really, can we, if we were able to observe either obviously the global signal or really the power spectrum, could we then learn which which dark matter model is preferred by our observations? So that's the goal. The problem is obviously that dark matter is not the only thing that changes the 21 centimeter signal. So there's a very large astrophysical parameter space, and you can see this here with this nice movie from 21 centimeter fast, where basically as you change these different astrophysical parameters, it will change 21 centimeter, change the 21 centimeter signal. We can see that showing up in the global signal in the power spectrum. This model here basically just contains population 2 galaxies. This has now been improved upon over the last few years, and there was a recent paper by Julian Muñoz showing which included the most sort of advanced population 3 galaxy formation model. So the problem is now that there are an awful lot of parameters, both astrophysical, and then now we want to add in these dark matter model parameters. It becomes very challenging to sample this parameter space to make, if we want to make forecasts for how well we could constrain all of these parameters given our observations. So what we've done is actually take a simpler approach than doing something like an MCMC, and we've used the Fisher matrix, approach. And so this gives us a way to efficiently estimate parameter uncertainties given a fiducial model and assumed observational noise. So the way this works is that to make the assumption that our likelihood is Gaussian, we can calculate the Fisher matrix from derivatives of our model. So basically here the Fisher matrix is a function of derivatives of our model with respect to the model parameters and including the observational noise. And we can then use the Fisher matrix, we can invert the Fisher matrix to find a lower bound on the covariance matrix. So the Fisher matrix will give us lower bounds on the parameter uncertainties. So the way that we do this in practice is we pick a fiducial model and then vary one parameter at a time to calculate these derivatives, and then invert the Fisher matrix to calculate the parameter uncertainties. And the real advantage here is that it's very fast because you don't need to calculate very many simulations or very many models at all. So we found that you actually can do this with just 2 times n, where n is the number of parameters, plus 1 models. You basically just have to pick the fiducial and then 1 model either side if you want to calculate the derivatives. And so this means you can really scale this up to a very large number of parameters. But obviously we want to test that it works. So we've been testing this against results from an MCMC that was presented by Park in this paper, Park 2019. So what you're seeing here are the 2D posteriors from the MCMC in the gray contours. This is just for a CDM model with population 2 galaxies. And then our forecasted uncertainties from using the Fisher matrix technique are the orange contours. So you can see we have really good agreement with the MCMC, both in terms of the actual direction of these degeneracies between parameters, but also in the absolute scale of the uncertainties. So we think we can now sort of use this to forecast into unknown territory. And so as part of this work, we've now updated 21 centimeter fast a bit, though I think I actually haven't pushed this yet. But we have added these ethos dark matter models through a parameterization of the matter power spectrum to 21 centimeter fast. And we've also now written a Fisher matrix wrapper for 21 centimeter fast. So if you want to do these kind of quick forecasts, it may be easier to use this Fisher matrix wrapper than, for example, running a full MCMC. And that's now it's on GitHub and mostly documented. And so now with this fast approach, we're able to make forecasts for a larger range of parameters. So what I'm showing you here, we have now taken this most up-to-date version of the fiducial 21 centimeter simulation, the evolution of structure simulation, and made forecasts for this whole range of both population 2 and population 3 galaxy formation parameters. And what we find is that if we assume moderate foregrounds and observing with HERA for 1 year of data, observing the full power spectrum, we would be able to measure, we predict that we would be able to measure both population 2 and population 3 galaxy parameters and X-ray parameters to around and sometimes less than 10% precision. So this is a nice, exciting forecast, especially that we think we'll be able to do a really good job of measuring population 3 parameters. And I think most of that comes from actually the very wide frequency range that we would be able to observe with HERA. And so you can really look back to high redshifts where those population 3 galaxies become important. And we then tried to make some forecasts for the dark matter parameters too. This part is still, I would say, a bit preliminary, but based on preliminary results, it seems like we could be able to distinguish warm dark matter from cold dark matter if the warm dark matter particle had a mass of less than about 50 keV, which is quite surprising. So this part is still a bit preliminary, and need to sit down and finish this off. But I think could be some pretty exciting predictions here. And so in summary, I've told you that the 21 centimeter signal contains information about early structure formation, and the timing of the structure formation really depends on the interplay between these astrophysical effects, but also on dark matter effects. And so we've included this ethos dark matter paradigm model within 21 centimeter fast, and found that it changes the amplitude and delays the 21 centimeter signal. And we think the upcoming 21 centimeter experiments, in particular, we forecasted experiments with HERA, could place constraints on both population 3 galaxy parameters, but also hopefully on dark matter parameters. And we've done this using this Fisher matrix wrapper for 21 centimeter fast, which you can find on GitHub. So I'm sorry that I couldn't be there live today, but I will be available on Slack to answer any questions. So thank you.
Maybe can share your screen. And if you have further question, as Charlotte mentioned, that you can just put it on Slack. So next talk is by the HERA group, and it's going to be about theoretical interpretation of first HERA upper limits. So Yuxian and others, you will have 15 plus 5 minutes for this talk. I will inform you when you have about 2 minutes or so left. Yeah. Please.
Yeah. Thanks. Right. Thank you. So, as the host was saying, that basically we are presenting the theoretical interpretation for the first HERA upper limit. So basically, the idea is I would present the results within the standard model, and after that, Stefan and Julian would follow up by expanding that with a focus on understanding, for instance, the extra cooling from dark matter or the radio background in addition to the CMB. And obviously, this work wouldn't be possible without the support from the entire HERA collaboration, so which is listed here. Just want to especially acknowledge the effort from Stephen Fernetto, who led the writing of this paper, which joined the results from different theoretical groups that we are presenting today. All right, so this is what I'm gonna talk about. So I'll have a very quick review of reionization 21 centimeter, and also highlight the HERA results that we are using for the inference. I would very quickly go through 21 centimeter fast and the Bayesian inference. Most of them have been mentioned already, and then I will show you some of the results. All right, so just to remind everyone that what we are doing here is to study the epoch of reionization using 21 centimeter signal. So this is an observable that, this is an observable of the neutral hydrogen spin temperature observed in contrast to the cosmic radio background, which in the standard model would be CMB. And the spin temperature basically changes between the background and the gas kinetic temperature depending on various process. And the kinetic temperature is predominantly determined by the heating and the Hubble expansion. But when the other two speakers are speaking, they would basically change the basic assumption. So they will consider additional radio background as well as extra cooling to change the gas kinetic temperature. So HERA is an interferometer array in South Africa, and it has been running for a while now. And so this temperature map basically shows you the observed range for HERA on the sky. And so for this type of for this time, we select the observers select these three fields, which are relatively cleaning from the foreground, and they did a very nice job beating the noise, and then they provide us with these upper limits for the 3 different fields, and using from 2 different bands corresponding to redshift 10 and redshift 8. All right, so in order to further model the 21 centimeter signal and get some of the summary statistics, such as the global signal and also the 21 centimeter power spectra, and then to compare against the observed upper limits, we use 21 centimeter fast. Charlotte already mentioned it already. So basically, it models the average property of galaxy and parameterize those properties as a function of halo mass. For instance, this several equation just shows you how we calculate the stellar mass, the UV luminosity, the photon budget for our non photon, and also the duty cycle of star forming galaxy. And by changing those variables, we are able to basically run hundreds of thousands simulation and calculate the power spectra to compare with the HERA result. We also have extra parameter for heating, because we basically assume the heating comes from high mass X-ray binary that scales with the star formation rate of your galaxy. So because this model is very fast, so we can do MCMC. So basically, the principle of MCMC is just you select a point in your high dimension parameter space. You follow the model you observable, you calculate your summary statistic, you calculate the likelihood, which gives you, which allows us to accept or reject the points. And then you do it multiple times. You can construct the posterior for your parameters, which is shown here as the bottom left panel, and also the posterior for some of your predictions. So in the next 3 minutes, I'm just gonna go through those predictions. So here there are 2 posterior, which is shown by these 2 different color. So basically they shows you the allowed range, the allowed models that are basically agree with the current observation. So both of them includes the high redshift UV luminosity function, as well as the CMB optical depth given by Planck, and the neutral hydrogen refraction observed using the quasar spectra. And you can see the posterior looks very similar. This is saying that the HERA is not constraining these observables. But if we look at the 21 centimeter signal, again, this is the global signal, and this is the power spectral for a given scale. So this is a little bit different from what we are familiar with normally. This is not the power as a function of the scale for given redshift. This is the power as at one particular scale as a function of redshift. So you can see that when we include the HERA limits, we are able to exclude a lot of model which has very high power compared to the HERA limits. And also the reason for those models to have a high power is because they have very weak heating. I just want to remind people that the reason for the temperature to stop going down and going up is because you have heating resources. If we do have some sort of a heating in the early universe, the absorption trouble will become shallow and shift to higher redshift. I'm also showing here some of the recent results from other instruments, and you can see that HERA actually has the lowest limit so far. And because the heat in this model, we assume heating comes from mostly the high mass X-ray binary. We can actually compare their properties when we include or doesn't include the HERA upper limits. So the without HERA limit is this orange curve, which you can see there's no limit on this X-ray parameter. But when we do include it, HERA is telling us that the X-ray luminosity of the high redshift galaxy has to be higher compared to low redshift metal enriched galaxy, which is shown here as the vertical solid line. This is consistent with this theoretical expectation for metal-free galaxies, which is shown here as a dashed dotted line. And in the end, I just want to say a little word about the RGM temperature. This is the posterior of the RGM kinetic temperature at redshift 8. And you can see that without the HERA limit, most of our model actually is saying the IgM is sitting just above the adiabatic cooling limit. However, if we do include the Hera limit, we see that the IgM has to be heated to at least 10 to 1,000 Kelvin. And this is my summary. And then I'm going to switch to Julian.
All right, thank you, Yuxian. And yeah, so I will now talk about an analytic view of these limits, sort of building up on the 21 centimeter fast simulations. And the goal of doing these sort of analytic things is first to get intuition, and second to explore and broaden our assumptions. And this will be very skeletal because we only have 5 minutes. But if you have more questions or want to chat, please, reach out. So I will talk about this plot essentially, like limits on the spin temperature versus redshift, where as Yuxian showed, 21 centimeter MC, which is built 21 cm fast, can put us in limits. So what we'll do first is a very simple thing, a very silly thing, which is assume that the 21 centimeter fluctuations are biased with respect to matter density. And in some regimes, that is true. We call this density-driven models. But in most regimes, it will actually only be a simplification. But this allows us to very simply translate limits on the power spectrum to limits on this bias. And a smaller spin temperature translating to a larger B21, a larger bias. So essentially moves the curve up and down, and eventually it will be ruled out. So by doing this sort of very simple analytic approach, we can get limits on the spin temperature. And this is what as analytic density-driven models give you as limits. And as I said, the whole point of this talk is to see how in these very simple models that we understand very well, our results change with our assumptions. So the first thing you can do is compare 21 centimeter MC and see that roughly they agree at the order 1 level, which that is a good encouragement. And these are the 3 assumptions we're going to check. First, we're going to see that how resistive distortions change things, then how density and ionization correlations change things, and finally, what happens if there's extra cooling, which cannot be done in standard 21 cm fast yet. So first, talk about resistive distortions. The way these play in is that the velocity, the line of sight velocity, is part of 21 centimeter signal and is given by a mu square, which is a cosine with the line of sight times delta. So varying this mu varies the size of the 21 centimeter fluctuations. Setting it to 0 is ignoring RSDs. Setting it to 1 is considering only line of sight modes. And the usual thing we do is take the spherical case, which corresponds to about 0.6. Now, what you see here is the limits change a lot in these models when you change mu. And in particular, we should be in the mu equals 1 case, which is line of sight modes given the wedge. So this is a shortcoming of our current analysis. That is something that we're trying to improve for next Hera data, is actually take the line of sight modes that we see with the wedge. For the densities, I'm showing this super complicated equation, but don't worry too much about it. Jordan Miroka and I, mostly Jordan, implemented a model of bubbles that correlate with density. Sorry, to try to compare the 21 centimeter MC results with this phenomenological bubble model, and we got comparable results. And if you want to hear much more about this, please reach out to Jordan or myself. And finally, the last assumption, which is my favorite one, is what happens if there's extra cooling. And with that, what I mean is that instead of the standard adiabatic spin temperature, which is the black line, you have something else that cools the gas. So you have cooling, for example, by interacting with merely charged dark matter, which is what we propose to explain the edges anomaly, because edges requires the spin temperature to be below this blue line. As you can see here, the red line is well below edges, but it's also well below Hera at redshift 10. And we could only get these limits with these sort of analytic approaches because this is below the adiabatic cooling line. So the standard astrophysical scenarios do not reach below the black, at least yet. Once we implement these models in 21 cm fast, they will. So Hera is telling us that these models are ruled out, at least unless something happens between redshift 17 and redshift 10, which we expect. According to the edges signal, the gas should be heated at some point. But this gives us extra information. And of course, once we can move Hera all the way to redshift 17, once we have low frequency data, we'll be able to put dark matter constraints and really test the edges detection. So to conclude this section, I'll leave to Stefan. Analytic models allow us to explore assumptions, and in particular, redshift space distortions are the trickiest, and we need to work on them. The different models broadly agree. I think Stefan will touch on this later. And finally, if dark matter explains edges, you need heating by redshift 10 rather than by redshift 8. So it tightens a little bit your constraints on when you need the heating to occur. So Stefan, please take over.
Yeah, thank you. And as Yuxian said earlier, I'll talk about the case where we consider that the background that we see might not be just the CMB, but also contain some additional radio sources, such as radio galaxies that emit an inhomogeneous radio background in the universe, or a simple model of a simple homogeneous synchrotron background from some exotic sources, say some dark matter. And what this essentially does is it lifts up this kind of radio background that you have in your 21 centimeter signal. So it increases the contrast between your radio background and your gas temperature, and thus allows it to have a much larger 21 centimeter brightness signal. So to illustrate this point a bit, what I've shown here at the bottom right is the power spectrum that we get. In the dashed line, you see the highest power spectrum we get if you don't include any additional radio sources. And as the colored line, you see our simulations including radio background. And of course, we get a much larger power spectrum, which means we can rule out a big part of this additional parameter space. And we do this also with semi-numerical simulations. So Anastasia has mentioned them this morning in a lot of detail. So I'll just briefly say it's slightly different to 21 centimeter fast, but the methods were similar. And of course, we have an additional parameter that tells us how much of this radio background we include. And the other main difference to the analysis that Yuxian with 21 centimeter fast did is that we don't run an MCMC run using our simulations, but we use an emulator, which essentially interpolates some existing simulation runs. So the benefit of that for us is we only have to do about 10,000 simulation runs, use this as training data for a neural network that essentially then we can use for the MCMC run. This comes with a big benefit of saving us a lot of computation time. Although the downside, we get about a 20% error essentially from this emulator, which is fine for now because observational uncertainties are much larger than these emulator problems.
You have about 2 minutes.
To the results, I'll start with a kind of big triangle plot of all our parameters. And I don't want you to look in the details in particular. I think the main takeaway is that with Hera alone, many parameters can't really be constraints in these, or even in this radio models. So saturation rate, etc., don't have a big effect, except for these two parameters here. So the X-ray efficiency and the efficiency of the radio galaxies. So if you look at this kind of zoomed out 2D posterior plot, where in color you see the value of the posterior PDF, and you see this white corner over here, which is essentially kind of excluded, which corresponds to models that have a low X-ray efficiency, so a cold IgM, and a high radio efficiency, so a big background. So these are the models that have this kind of large contrast and exceed the Hera limits. And to give you some context, these orange yellow lines correspond to about 25% of today's X-ray efficiency of galaxies, and 400 times more radio efficiency than today. So those are quite high values. Similarly, the other model I mentioned, the homogeneous synchrotron radio background, corresponds to about 5 times the level of radio that you would get from the CMB. This is quite large, but still not as large as the upper limits we have from experiments like Arcade 2 and LWA, which corresponds to more like 50% of the CMB at those low frequencies. To give a bit more detail on this last point, so comparing our relative, sometimes extreme models to kind of today's observations, we have for X-ray, we have the unresolved X-ray background from Chandra, which gives us an upper limit on the amount of X-ray we can produce, which is proportional to 2 of our parameters, as well as the limits from RK2 that I mentioned earlier, giving us a limit on the amount of radio background. And in this kind of plot here, I show you in X all the models that we have in our simulations that are already ruled out by Chandra, and in anti-circles, the ones that are ruled out by LWA. But you still see there's a large amount of parameter space that is not ruled out by these models and can be significantly constrained by Hera. So you see these orange models are kind of excluded by Hera at a few sigma, and we kind of cut into this remaining parameter space. And finally, a bit correlated to what Julian said earlier, I can tell you something about the temperatures in the IgM as opposed to just model parameters. So what you see here in this plot are the 2D posteriors and prior for the radiation and gas temperature. And essentially in yellow, you see the prior for our models, for our simulations, compared to the posterior in blue. And you see essentially the models that are ruled out are the ones that have a too high of a radiation temperature or too low of a spin temperature. So when the ratio of radiation to spin temperature is bigger than 10, roughly, we can exclude those models. So this is very kind of intuitive to what Julian said. The upper limit on the 21 centimeter signal corresponds to a lower limit on the spin or gas temperature. And this is also what I leave you here in my summary. On the right-hand side, you see a plot of all these methods giving constraints on the spin temperature from here. Yeah, thank you. And we are all happy to answer questions now.
Thank you all the speakers, Julian, and Stefan, for this concise overview of the interpretation. And now I'll ask other participants to ask some questions. You can post them on Slack, or you can raise hand and I can try to unmute you. Okay. I don't see any hands. So a very nice question to all of them. So like next cycle of Hera observations. So which front will get like much more benefit from the next cycle of the data analysis that you are currently doing?
Yuxian, do you want to take this?
Sorry, so you were asking which front? I didn't really understand.
Means like you are going through different sort of interpretations, right? But which front you are going to make much more progress?
I think we are all approaching the question from different angles. So I can speak for our model. So preliminary result will show that the new results that we hopefully to publish soon will help better constrain, for instance, the X-ray parameters that I just discussed it, and also put on much RGM spin temperature and also the kinetic temperature. But I believe all of us will get a tighter constraint, but we are approaching the question from different angles. So
I'll say that for dark matter stuff, you definitely want to go to the highest redshift that you can before X-rays. In which case, I think you really want to use the lower frequency data they're collecting now, like it's been collected recently. So that then you will get a huge gain.
I think for our models, the thing we saw earlier that if we don't have any radio background, it's very close to the current limits. So if you get a bit below the limits, I think we can start to constrain even more, like models even better if we don't have, like even without the radio background.
Okay, thank you. So we have a question from Harold. So are the constraints on the spin temperature absolute? That is, they hold for all values of the other parameters?
So I think it might depend on which of these, but I think in most cases it's marginalized over the other parameters. So these constraints are 95% lower limits on TS over T radio in our case. And I think just TS in your case, marginalized over the remaining parameters.
Yeah, I think the exception is the analytic approaches where you have to assume a particular value, say, of the ionization, like from 0.5 to 1, you can see how it varies. And there's, by the way, one more panel with the one led by Jordan Miroca, where he did this bubble model, and then he did marginalize over XH of the ionization fraction. So in general, yes, it's marginalized over.
Yeah, I think for us, the spin temperature is not a free parameter, it's actually a forward modeled parameter. So it's actually a prediction, not a model. So it's a prediction, not a model parameter.
Okay. Any more questions? Please put them on Slack. Okay, maybe people will ask you guys later on. Please just have a look at the Slack thread sometime. Okay, so with these, we conclude this session. I would like to thank all the speakers of this session for their excellent talks and making the time. And so the next session will start from 1500 hours GMT, and it will be on analytic and numerical modeling of the signal. I think we will break now and we will come back in the next session. And by the meantime, if other organizers have any announcement they would like to make, or we will close the session.
I think it's all good. Thank you so much.